What if the first faster-than-light ship did not open a doorway to the stars, but opened a crack in time itself? Imagine a spacecraft leaving Earth one quiet evening, while everyone on the ground watches the engines ignite and expects a miracle. It does not crawl away like a rocket. It does not spend years crossing the empty dark between worlds. It bends distance, breaks the rule that seems to hold the universe together, and reaches another star before the light from its own departure has fully crossed the solar system. At first, that sounds like victory. Then the clocks begin to disagree. Messages arrive in the wrong order. A signal sent after the ship leaves appears to reach its destination before the launch has happened. Astronauts return with memories that do not fit the calendars on Earth. A journey that was supposed to defeat distance begins to threaten something deeper than distance: cause and effect. Before we begin, if you enjoy calm, deep journeys through space, take a moment to subscribe, leave a like, and write in the comments where you are watching from and what time it is for you right now. It is always strange to remember that people can be listening to the same story from different cities, different countries, and different nights on Earth. Tonight, you are watching the Just About Space channel, talking about what would happen if humans actually traveled faster than light. And to understand why this question is so powerful, we have to begin with a very uncomfortable truth. The speed of light is not just the speed of light. It is not only the speed at which sunlight moves through space. It is not only the speed at which a laser beam crosses a room. It is not only a number written in physics books, close to 300,000 kilometers per second. It is the speed at which reality allows information to travel. It is the speed at which changes can spread through the universe. If the sun disappeared, Earth would not know instantly. For about 8 minutes, our planet would continue moving under the gravitational influence of a star that was already gone, because even gravity does not update the universe instantly. The change would travel outward at the speed of light. That is the first reason faster-than-light travel is not just a transportation problem. It is a communication problem. It is a time problem. It is a question about how events are allowed to connect. When people imagine traveling faster than light, they often picture a simple race. A beam of light leaves Earth. A spaceship leaves beside it. The ship somehow accelerates harder, passes the beam, and arrives first. In that picture, light is just the fastest runner on the track, and faster-than-light travel means building a better runner. But relativity tells us that the track itself is stranger than that. Space and time are not two separate backgrounds. They are woven together into space-time. A distance through space and a distance through time are connected. When an object moves faster through space, its motion through time changes from the point of view of other observers. Near the speed of light, clocks no longer agree in the ordinary way. Lengths shrink along the direction of motion. Energy requirements rise. The universe does not behave like a stage where everyone shares the same invisible master clock. This is where the first trap appears. For slow motion, the universe feels simple. If you walk across a room, everyone can agree that you crossed it after you started. If a car drives down a road, people standing nearby might disagree about small details, but not about the basic order of events. First, the car is here. Then, it is there. At everyday speeds, time feels universal. At cosmic speeds, it is not. Special relativity says that different observers moving relative to each other can disagree about whether two distant events happened at the same time. This does not mean they disagree about everything. If one event causes another, the order is protected as long as the cause travels at light speed or slower. A flash hits a sensor. The sensor reacts. Everyone can agree the flash came first, because the connection between the two events stayed inside the allowed structure of space-time. But if you allow something to move faster than light, you can create situations where one observer sees the effect happening before the cause. That is the frightening part. Faster-than-light travel does not only say, we arrived quickly. Under ordinary relativity, it can also say, we arrived before the story was supposed to allow us to arrive. To see why, imagine two planets far apart. Earth sends a faster-than-light message to a colony world. From Earth's point of view, the message simply travels very fast. It leaves today and arrives almost immediately. Nothing sounds impossible yet. Now imagine the colony world is moving relative to Earth, as real planets, stars, and spacecraft always are. In the colony's frame of reference, because of relativity, the timing of distant events is sliced differently. The message that Earth considers a fast-forward signal can appear, in the colony's frame, to arrive before Earth sent it. If the colony then sends a faster-than-light reply back to Earth, under the right conditions, that reply can arrive before the original message was sent. Now the universe has a problem. Earth can receive an answer to a question nobody has asked yet. A person could be warned not to send the first message. If they obey the warning, the reply is never sent. If the reply is never sent, the warning never arrives. The loop destroys itself. This is why physicists treat faster-than-light travel with such caution. It is not because scientists are trying to keep space travel boring. It is because the speed limit is tied to causality, the rule that causes come before effects. Break that rule carelessly, and the universe stops behaving like a sequence. It becomes a machine that can contradict itself. And yet, the story is not as simple as saying faster-than-light travel is absolutely impossible meaning of the phrase. Because general relativity, the deeper theory of gravity, allows space-time itself to curve, stretch, compress, and evolve. The universe already contains regions where distant galaxies recede from us, faster than light. Not because those galaxies are locally flying through space faster than a photon, but because the space between us and them is expanding. This is not the same thing as a spaceship turning on an engine and breaking the local speed limit. It is stranger. Locally, in a small region of space-time, the speed of light still acts like the limit. A galaxy far beyond our reach is not racing past its local neighbors faster than light. Instead, the metric of the universe is changing. Space itself is growing between distant regions, and that growing distance can increase faster than light could cross it. This distinction matters. A human being inside a spaceship cannot simply push a throttle and accelerate through ordinary space until the speedometer reads faster than light. But in theory, one might ask whether space-time could be shaped so that a ship arrives at a destination faster than light would, while the ship itself never locally outruns light inside its own small patch of space. That is the basic dream behind the warp drive. Instead of moving the ship through space faster than light, contract space in front of the ship and expand space behind it. Place the ship inside a bubble of relatively normal space-time. Let the bubble move by changing the geometry around it. From the outside, the destination is reached too quickly. From inside, the travelers may feel almost still. This idea became famous through science fiction, but it also has a real mathematical version. In 1994, physicist Miguel Alcubierre showed that Einstein's equations allow a space-time geometry with some of these properties. The result was not a practical engine. It was not a blueprint. It was a solution to equations, a way of saying that the mathematics of general relativity does not instantly forbid every kind of apparent faster-than-light motion. But the price was enormous. The original Alcubierre warp drive required exotic matter, or negative energy density, something not known to exist in usable amounts. It also raised severe questions about stability, control, radiation, horizons, and whether the occupants could even create or steer the bubble from inside. Later researchers explored modified warp metrics, lower energy requirements, subluminal warp bubbles, and models that try to avoid some of the worst problems. But no one has built a warp drive. No one has shown a practical way to generate one. No known spacecraft technology is close to this. So if humans actually traveled faster than light, it would mean one of two things. Either we discovered entirely new physics that changes our understanding of causality, energy, and space-time, or we found a loophole inside the physics we already know, one that uses the shape of space-time rather than ordinary motion through it. Both possibilities are terrifying in different ways. The first possibility means the universe is not as stable as we thought. The second means the universe is stable, but only if we handle it with extraordinary care. Now, let us slow down and ask what faster-than-light travel would look like before it became a civilization-changing technology. The first FTL trip would probably not begin as a comfortable passenger flight to another star. It would begin as an experiment filled with uncertainty. There would be no windows showing stars streaking past like lines of white fire. That image belongs mostly to cinema. At real relativistic speeds, light itself changes. Stars ahead are compressed into a brighter, bluer region. Light behind shifts redder and weaker. Radiation becomes dangerous. Interstellar dust becomes a high-energy hazard. If the ship used something like a warp bubble, the view could be even stranger. The outside universe might be distorted by the curvature of space-time around the vessel. Light from ahead could be bent, compressed, blue-shifted, or hidden by horizons depending on the exact geometry. The travelers might not see a clean road through space. They might be inside a region where the normal connection between inside and outside becomes limited. A warp bubble is not simply a transparent car moving across a map. It is a moving distortion in the map. That means navigation would become one of the first impossible-sounding problems. If you are traveling to a star 4 light years away, you need to know where the star will be when you arrive, not where it appears to be from Earth. You need to account for its motion, the motion of your departure system, the motion of the galaxy, the curvature created by masses along the way, and the fact that the information you have about the destination is already years old. At ordinary speeds, this is difficult. At faster-than-light speeds, it becomes dangerous. You could arrive where a star used to be. You could overshoot the safe region by astronomical distances. You could emerge inside a debris field, too close to a star, or in a gravitational situation the mission planners did not predict. The faster the trip, the less time there is to correct mistakes while traveling. An error that would be manageable over decades might become fatal in seconds. This is one of the quieter horrors of faster-than-light travel. It makes the universe feel smaller, but it also gives every mistake less time to unfold. If humans discovered a working FTL method, the first missions would probably be robotic. No space agency or civilization would send people into the first uncontrolled distortion of space-time if machines could test it first. A probe might be aimed at the outer solar system, then perhaps at the nearest stars. It would carry clocks, radiation sensors, cameras, gravitational instruments, and communication systems designed to answer one simple question. Did it really arrive faster than light? But even measuring that would be delicate. You would need synchronized clocks. You would need to know the exact path. You would need to distinguish actual superluminal travel from a measurement error, a signal processing artifact, or a misunderstanding of distances. Science has seen false hints before. In 2011, an experiment appeared to detect neutrinos traveling faster than light, but the result was later traced to equipment problems. That episode became a warning. When an experiment seems to break a foundation of physics, the first suspect is not the universe. The first suspect is the cable, the clock, the calibration, or the assumption. A real FTL discovery would demand overwhelming evidence, multiple instruments, independent replication, tests in different directions, results that survive years of skepticism. It would not become accepted because someone announced a miracle. It would become accepted only after the ordinary explanations failed. And when they failed, the world would change. At first, the public might celebrate the way people celebrated the first moon landing, but the deeper consequences would take longer to sink in. Faster-than-light travel would not only change space exploration, it would change astronomy, defense, economics, philosophy, and our sense of isolation. The nearest star system, Alpha Centauri, is about 4.37 light-years away. With chemical rockets, it is not a human destination in any practical sense. With the fastest spacecraft humans have launched, the trip would take tens of thousands of years. Even advanced fusion or laser sail concepts still face enormous engineering challenges and travel times measured in decades or longer. But if a ship could cross that distance in months, weeks, or days, the emotional geography of humanity would collapse. The stars would no longer be only lights. They would become places. Not easy places, not safe places, but places that could be visited, surveyed, mapped, perhaps one day reached by human beings. The first major shock would be how empty those places are. Science fiction often fills star systems with colorful worlds, close encounters, ruins, civilizations, and convenient destinations. Real star systems may be far more silent. A faster-than-light probe could arrive at Alpha Centauri and find no habitable world around the main stars. It might find harsh planets, small icy bodies, unstable radiation environments, and distances that remain huge even inside a neighboring system. FTL would not make space cozy. It would only make the first wall fall. After that, the true scale would still be waiting. A star system is not a single point. It is a region of space, billions of kilometers wide. Even after arriving faster than light, a ship might still need to travel through that system, using slower local propulsion. The warp mechanism might not be safe near stars or planets. It might require calm, empty regions far from strong gravity. If so, travelers could appear at the edge of a system and still spend months approaching the world they came to study. The arrival would be only the beginning. This is important because it keeps the idea grounded. Faster-than-light travel does not magically erase physics. It does not create food, air, fuel, or protection. It does not guarantee a planet is livable. It does not remove the need for life support, shielding, navigation, energy production, repairs, or human endurance. It solves one problem: the distance between stars. But that one problem is so enormous that solving it would make every other problem newly visible. If humans actually traveled faster than light, the first true explorers might find that the galaxy is more reachable than we thought, but less welcoming than we hoped. They would arrive at red dwarf systems, where planets are locked in eternal day and night. They would visit young stars surrounded by debris and radiation. They would approach old white dwarfs, surrounded by the remains of dead planetary systems. They would pass through molecular clouds, where new stars are forming. They would map rogue planets drifting without suns. They would inspect worlds that telescopes can only hint at today. And each new destination would bring a strange, emotional shift. For all of human history, the stars have been symbols of distance. They have been unreachable backgrounds to our myths, our calendars, our religions, and our navigation. Faster-than-light travel would turn them into geography. The sky would stop being a ceiling of lights and become a set of possible roads. But roads can also lead into danger. The second shock would be that faster-than-light travel might make isolation worse before it makes it better. That sounds backwards. If we can reach the stars, should we not feel less alone? Maybe. But imagine the first 100 nearby systems are surveyed. No cities, no radio beacons, no obvious biospheres, no ruins, no signals waiting in the dark. Just stars, planets, ice, rock, gas, dust, and silence. Today we can tell ourselves that maybe the universe is full of life, but it is simply too far away to detect. If FTL allowed us to check nearby systems directly and still find nothing, the silence would become more personal. It would no longer be a limitation of distance. It would be a result. That is one of the unsettling parts of becoming powerful. Every new ability removes an excuse. A civilization with telescopes can wonder. A civilization with probes can test. A civilization with faster-than-light ships can no longer hide behind the idea that maybe we just cannot reach far enough. At least, in the local neighborhood, it could go and look. If the answer was still silence, it would change us. But if the answer was not silence, that would change us even more. The first confirmed alien biosphere would become the most important discovery in human history. Not necessarily intelligent life, not necessarily technology. Even microbial life beneath ice or in an ocean world around another star would prove that life is not unique to Earth. With FTL, sample return missions could become possible. Instead of receiving data centuries later, or never at all, scientists might compare living chemistry from multiple worlds within a human lifetime. That would transform biology. It might reveal life with DNA-like molecules, or something completely different. It might show whether evolution repeats patterns. It might show whether photosynthesis, cells, metabolism, and complex organisms are common outcomes or rare accidents. It might even show that some planets are alive in ways we do not currently imagine. But that would also create danger. Faster-than-light travel would raise the stakes of contamination enormously. A slow robotic mission can be sterilized and carefully controlled. A network of rapid interstellar travel increases the risk of moving microbes, spores, chemicals, or engineered organisms between worlds. Humanity would need strict planetary protection rules not only for science, but for survival. A harmless Earth organism in one environment might become destructive in another. Alien chemistry might be dangerous to us without being malicious. A sample that looks dead could become active under the right conditions. A planet with its own biosphere could be damaged by our arrival before we even understand what is there. The dream of FTL travel often focuses on escape and exploration. But if humans actually had it, restraint would become as important as ambition. A faster ship does not make us wiser. It only gives our mistakes a longer reach. Now, there is another side to this question, one that is even stranger than alien worlds or interstellar maps. What would faster-than-light travel do to time for the people on board? For ordinary near-light travel, relativity gives us a clear effect. The faster a ship moves relative to Earth, the slower its onboard clock appears to run from Earth's perspective. This is time dilation. If a ship traveled close enough to the speed of light, astronauts might experience a much shorter journey than people waiting at home. They could cross huge distances while aging less than those who stayed behind. This is not science fiction. Time dilation has been measured with particles, clocks, aircraft, satellites, and high-speed systems. GPS satellites must account for relativistic effects, or their positioning would drift. Relativity is not an optional idea. It is built into technology. But faster-than-light travel is different. If a ship somehow exceeds the normal light speed limit by moving through space-time in the ordinary way, relativity equations become deeply problematic for massive objects. The energy required to reach light speed rises without limit. Beyond that barrier, the usual descriptions stop applying to normal matter. If the ship uses a warp bubble, the astronauts may not locally move near light speed at all. They might feel little acceleration. Their clocks might tick normally inside the bubble. To them, the trip could seem calm, almost disturbingly calm, while the outside universe sees an arrival that should not have happened so soon. This creates a strange emotional possibility. The most impossible journey in human history might feel quiet. No roaring engines, no stars becoming streaks, no bodies crushed into seats, no heroic sense of speed, just a controlled room, instruments humming, and a view of space that may be too distorted to trust. The terror would not come from motion. It would come from knowledge. The crew would know they are inside a machine that changes the relationship between here and there, now and then. They would know that if the bubble fails, no rescue could arrive in time. They would know that if the math is wrong, the destination could become unreachable. Or worse, the arrival could produce effects no one predicted. One concern often discussed in warp drive physics is the accumulation of particles or radiation around a moving bubble. If space-time distortion sweeps up matter or blue shifts radiation at the front edge, releasing or interacting with that energy could be dangerous. Different models have different details, and many remain speculative, but the broad warning is clear. Interstellar space is not perfectly empty. It contains hydrogen atoms, dust grains, cosmic rays, magnetic fields, photons, and background radiation. At normal speeds, these are hazards. At extreme effective speeds, they could become catastrophic. A single dust grain at relativistic impact energies can behave like an explosive. Radiation from the cosmic microwave background, starlight, and interstellar particles could be shifted into more dangerous forms depending on the motion and geometry. A faster-than-light ship would need more than an engine. It would need a shield against the universe itself. This is where the romance of FTL begins to darken. We imagine cutting travel time, but every shortcut in physics has a cost. If the cost is energy, we must gather it. If the cost is exotic matter, we must discover it. If the cost is causality, we may not be allowed to pay it. If the cost is radiation, navigation, or stability, the first trips might be far more dangerous than the long, slow journeys they replace. And then, there is the question of communication. If ships can travel faster than light, can messages travel faster than light too? If the same technology can send signals, then interstellar civilization becomes possible in a completely different way. Colonies could speak with Earth in real time or near real time. Scientific data could flow across light years without waiting years for a reply. A crisis in another system could be reported quickly. A network of worlds could exist as a political and cultural entity instead of isolated islands. But if messages remain limited to light speed while ships can somehow move faster, the situation becomes bizarre. A spacecraft could physically arrive before its own radio announcement. A visitor from another star could land before the signal saying it had departed. A colony ship might return with news from a system whose light has not yet shown Earth what happened there. This would make history difficult to organize. Astronomy is based on looking into the past. When we observe a star 100 light-years away, we see it as it was 100 years ago. Faster-than-light travel could let us visit places before their light has delivered their current image. We might stand near a star and see its present, while Earth still sees its past. The galaxy would become filled with layers of time. Earth-based telescopes would show old versions of systems that explorers had already visited in their current state. A planet seen from Earth as a young volcanic world might have already cooled or changed by the time a ship arrives. A supernova visible in our sky might have happened long ago, while a faster-than-light expedition could, in principle, reach regions affected by the explosion before the light reaches us. This does not mean travelers literally outrun every form of history in a simple way. It depends on paths, frames, and the mechanism used. But culturally, it would feel like time had become uneven. The sky would no longer be the best record of what is happening. Ships might become the faster record. That alone would change astronomy. Today, telescopes are our main way of knowing the universe. With FTL travel, astronomy becomes partly fieldwork. Instead of only interpreting light, scientists could visit the source. They could measure planets directly, place instruments around black holes, sample interstellar clouds, study exoplanet atmospheres up close, and watch stellar processes from nearby safe distances. But the word safe would always be conditional. Getting close to a cosmic object is not the same as understanding it. A black hole does not become harmless because you arrived quickly. A neutron star does not become gentle because your engine is advanced. A supernova remnant does not stop producing radiation because your civilization is brave. FTL would expand our reach, but it would also tempt us toward environments that were once safely unreachable. Some places in the universe may be better left remote. That is another terrifying consequence. A technology that makes impossible destinations reachable also makes lethal destinations reachable. Human beings are not only explorers, we are curious, competitive, impatient, and sometimes reckless. If faster-than-light travel existed, someone would try to go closer, faster, deeper, farther. Someone would build a private mission to a black hole. Someone would attempt to skim a neutron star's magnetosphere. Someone would race to an exoplanet before the official survey is complete. Someone would ignore quarantine rules. Someone would treat the galaxy like a challenge instead of an environment. The first FTL age might be full of wonder. The second might be full of accidents. A civilization that can cross stars needs laws that think in light years. It needs emergency protocols for places Earth cannot see in real time. It needs ethical rules for living worlds. It needs navigation standards. It needs limits on weapons. It needs agreements about who can claim what, who can land where, and what must never be touched. Because faster-than-light travel would not arrive alone. Every transportation revolution changes power. Ships changed empires, railways changed continents, airplanes changed war and trade. The internet changed information. A true FTL drive would change the meaning of territory itself. Today, Earth is one world. Space agencies and companies compete, but our civilization is still tied to one planet. If the stars become reachable, humanity could split across multiple systems. At first, that sounds like survival. If Earth suffers a catastrophe, other settlements might endure. The species becomes harder to destroy. But separation can also create divergence. Colonies around different stars might develop different cultures, laws, languages, economies, and identities. If communication is fast, they might remain connected. If travel is faster than communication, or energy limited, connection could be uneven. Some worlds might feel independent within a generation. Others might depend on Earth for technology and expertise. Political tension would follow the ships. FTL could save humanity from being trapped on one planet. It could also carry human conflict into the galaxy. And if causality problems are real, the danger could go even deeper. A weapon that uses faster-than-light signaling or travel might not behave like an ordinary weapon. It could appear without warning. It could bypass the usual delay that distance provides. It could make defense nearly impossible. If FTL allows information to loop backward in time, under certain conditions, then even the concept of an attack could become tangled with prediction and prevention. This is one reason a real faster-than-light discovery would be treated not only as a scientific breakthrough, but as a security crisis. The same engine that carries explorers to another star might carry something much darker. Any civilization that builds it must decide whether the galaxy becomes a shared frontier or a battlefield with no natural distance left to slow violence down. Still, the possibility is too powerful to ignore. Because the distances are so severe, without faster-than-light travel, the universe is accessible mostly through patience and light. We can send probes slowly. We can build telescopes. We can listen. We can watch ancient photons arrive after crossing cosmic distances. But our bodies remain trapped near one star. Even Mars is difficult. The nearest stars are beyond any ordinary human journey. FTL is the dream of turning cosmic time into human time. It says a star is not only something your descendants might reach after centuries. It says you might go, Arrive, look around, and come back with a memory. That is why the idea refuses to die. Even when the physics says no, imagination returns to it. Even when energy requirements look absurd, someone checks the equations again. Even when exotic matter seems impossible, researchers ask whether the geometry can be changed. Even when the answer remains no practical path, the question keeps its grip on us. Because faster-than-light travel is not really about speed. It is about loneliness. It is about whether intelligence is forever confined to small islands of time around its birthplace. It is about whether the sky is a wall or a map. And it is about whether the universe built a door somewhere inside its own rules. Now, before we go deeper into what an actual FTL journey might do to Earth, to explorers, and to the structure of human civilization, we need to look more closely at the three great versions of the dream. The first version is brute force. Just go faster. Accelerate a ship until it reaches near light speed, then somehow cross the barrier. This is the simplest idea in imagination and the hardest in physics. For any object with mass, approaching light speed requires more and more energy. The closer you get, the more the energy requirement grows. Light speed is not a normal finish line. It is an asymptote, a boundary that massive objects can approach but not reach by ordinary acceleration. Even before reaching that boundary, the engineering becomes overwhelming. The ship must carry or collect enormous energy. It must shield itself from interstellar particles. It must handle time dilation. It must brake at the destination. It must keep people alive for the journey. And if anything goes wrong at extreme speed, the energy involved is enormous. Near-light travel might be possible in some future with technologies far beyond ours. Faster than light by brute force appears forbidden. The second version is the shortcut. Do not move faster than light through space. Make the path shorter. This includes wormholes, hypothetical tunnels through space-time connecting distant regions. If a stable, traversable wormhole existed, a traveler might pass through it and reach a distant place faster than a light beam traveling through normal space outside the wormhole. Again, locally, the traveler need not outrun light. The trick is geometry. But wormholes come with their own problems. They may require exotic matter to hold open. They may be unstable. They may create time machine-like situations if their mouths move relative to each other. They may collapse, radiate, or become impossible to control. We do not know whether traversable wormholes exist in nature. We do not know how to build one. We do not know whether quantum gravity permits them in the way science fiction imagines. Still, the shortcut idea is powerful because it reveals something important. The light speed limit applies locally through space-time, but general relativity allows space-time itself to have shapes that make distance less straightforward than it seems. The third version is the warp bubble. Do not shorten the road by digging a tunnel. Move the road, contract space in front, expand it behind, and carry a ship inside a protected region. This is the Alcubierre-style idea and its many descendants. It feels closer to the popular image of a starship, but it is also filled with theoretical difficulty. The bubble must be created. It must be controlled. It must not destroy the destination. It must not trap the crew behind horizons. It must not require impossible energy. It must not release catastrophic radiation when stopping. It must obey whatever deeper laws quantum gravity imposes, laws we do not yet fully know. That last point matters. General relativity and quantum mechanics both work extremely well in their own domains. But we do not yet have a complete theory of quantum gravity. Warp drives and wormholes live in the borderlands, where space-time geometry and quantum energy conditions collide. That means the equations can suggest possibilities that nature may later forbid more deeply. This is why responsible scientists speak carefully. They do not say warp travel is around the corner. They say certain mathematical spacetimes can be written down, but the physical requirements may be impossible. There is a huge difference. A map of a bridge is not a bridge. A solution to equations is not an engine. But sometimes maps matter. They show where the boundaries might be. They force us to ask better questions. They reveal what kind of universe we would need in order to build the dream. And if humans actually traveled faster than light, it would mean that one of those boundary questions had been answered in the most dramatic way possible. It would mean distance had lost some of its power, but not all of it. Because the galaxy is not only far away, it is old, violent, changing, and largely indifferent to travelers. The Milky Way contains hundreds of billions of stars. Even with FTL, mapping it would take time. If a ship could cross 100 light-years in a day, the galaxy would still be a vast structure tens of thousands of light-years wide. There would be too many systems for any single civilization to understand quickly. The number of planets alone could be staggering. Some would be barren rocks. Some would be gas giants with complex moon systems. Some would orbit in dangerous resonances. Some would be hidden in dust. Some would drift alone between stars. Faster-than-light travel would not make the galaxy small. It would make it explorable. That is different. The first era might focus on nearby stars, Alpha Centauri, Barnard's Star, Wolf 359, Lalande 21185, Sirius, Epsilon Eridani, Tau Ceti. Each name would stop being an entry in a catalogue and become a destination with survey reports, hazard maps, and perhaps landing restrictions. Telescopes would guide the first missions, but direct visits would rewrite the data. Planets once known only by tiny dips in starlight would become worlds with weather. Spectral hints of water vapor, methane, oxygen, or carbon dioxide would become atmospheric measurements from orbit. Suspicious biosignatures would be tested. False positives would be exposed. Real biological worlds, if they exist, would be protected or exploited depending on the ethics of the civilization that found them. The dream becomes morally complicated very quickly. If we find a lifeless world, do we terraform it? If we find microbial life, do we leave it alone? If we find a primitive biosphere, do humans have the right to settle nearby? If we find intelligent life, do we reveal ourselves? Faster-than-light travel would turn philosophical questions into practical decisions. Distance currently protects us from answering too quickly. The stars are so far away that even our curiosity is slowed by physics. FTL removes that natural delay. It hands a young species access to ancient places and asks it to behave well. That may be one of the most terrifying possibilities of all. Not that we would find monsters in the dark, but that we would bring ourselves. Still, before we think about the ethics of an interstellar civilization, we need to understand what would happen to a single ship on a single faster-than-light trip. Suppose the first crewed FTL vessel is built in orbit around Earth, or far from the inner solar system, where a space-time distortion can be tested without endangering the planet. The ship is not shaped like an airplane. It has no need for wings. Its structure is designed around the drive geometry, power systems, radiation shielding, heat rejection, and emergency isolation. Around it may be rings, field generators, superconducting structures, or technologies we cannot yet describe because the physics is unknown. The crew boards, after years of robotic testing, every person on board knows they are not simply traveling. They are becoming part of an experiment about time. Mission Control begins the countdown. The destination is not a far star at first. It is probably a test point beyond the outer planets, perhaps outside the orbit of Neptune, then farther, perhaps beyond the heliopause. A human civilization does not start by warping to another star. It starts by proving it can leave, arrive, and return without turning the ship into debris or history into a paradox. The drive activates. Inside the cabin, perhaps nothing dramatic happens. The lights remain steady. The crew feels no crushing acceleration. There is no sense of being thrown through space. The instruments show that the external metric is changing, that distances are no longer behaving in the ordinary way. Outside, if an observer could somehow watch from a safe position, the ship might distort the light around it like a moving lens. Then, the test point appears on the navigation screen. The ship has crossed a distance light could not have crossed in that time. The room may stay silent for a moment, not because nothing happened, because too much happened. The crew would have to ask, what time is it on Earth now? What time is it here? What signals have arrived? What signals have not? Did the trip produce any delay, any radiation burst, any distortion trailing behind it? Did anything strange happen to the onboard clocks? Are the stars where the computer predicted they would be? And perhaps most importantly, can the ship go home? A one-way faster-than-light trip is not civilization. It is a disappearance with data. The true breakthrough is return. If the ship comes back safely, and if the timing makes sense, humanity has crossed one of the deepest boundaries in physics. But if the ship returns before it left, or appears to create any causal inconsistency, the celebration becomes fear. The first successful FTL mission would therefore be watched by physicists as much as by engineers. They would not only ask whether the drive worked, they would ask whether the universe protected causality somehow. Perhaps unknown physics prevents time loops. Perhaps the drive can only operate under conditions that avoid paradox. Perhaps there is a chronology protection mechanism, a principle that stops nature from allowing closed causal loops. Stephen Hawking once suggested such an idea in connection with time machines, though it remains unproven. If nature protects history, FTL might be allowed only in special forms. If it does not, then civilization would need to protect history itself. That sentence sounds impossible, but it is the kind of thought faster-than-light travel forces on us. Imagine a future where route planning is not only about distance and fuel, but about causality, safety. Certain trajectories might be forbidden because they allow message loops. Certain combinations of motion between star systems might create paradox risks. Interstellar navigation could require relativists, the way ocean navigation once required astronomers. A starship captain would not only avoid asteroids, they would avoid impossible timelines. Even if no literal time travel occurs, the operational rules could be severe. Drives may need to shut down near strong gravitational fields. Ships may need to follow approved reference frames. Communication may need delays inserted deliberately to preserve causal order. Interstellar law might include rules like no superluminal signaling between certain moving systems without synchronization protocols. The galaxy could become navigable only by respecting time as carefully as space. This is the part most stories skip. Faster-than-light travel is not just go anywhere. It is go anywhere without breaking the logical structure that lets events make sense. And if that sounds abstract, think of something simple. A child sends a message from Earth to a parent on a colony world. A faster-than-light relay delivers it instantly. The parent replies, "Under ordinary conditions, this is beautiful." Families separated by stars can speak. But if the geometry and relative motion allow the reply to arrive before the child sends the first message, then communication becomes unstable. Information can enter the past. Decisions can be influenced by outcomes they caused. The personal becomes cosmic. A technology built to keep people connected could become a machine for causality problems. Now, perhaps the actual universe prevents this. Perhaps any workable FTL method must preserve causal order in a deeper way. Perhaps warp bubbles, if possible, have limitations that stop paradoxes. Perhaps wormholes cannot be arranged into time machines because quantum effects destroy them. Perhaps faster-than-light travel will remain forever impossible for exactly this reason. But the question of what would happen if humans actually did it must include the possibility that time is not as forgiving as distance. And so, the first half of this journey leaves us with a strange picture. Faster-than-light travel would not simply give humanity the stars. It would force humanity to confront the hidden architecture beneath the stars. The speed of light is not a speed bump. It is woven into causality, measurement, communication, energy, and the way different observers divide space from time. To go beyond it would mean touching the rules, not just the distances, not just the engines. The rules. In the second half of this story, the question becomes even more human. What would an FTL civilization actually do? How would Earth change if the stars became reachable? What happens to war, exploration, alien life, religion, economics, colonization, and the future of the species when the galaxy is no longer a distant painting, but a dangerous territory? And there is one final question waiting beneath all the others. If faster-than-light travel is possible, why has no one used it to reach us? Before that question can be answered, there is one practical detail that often hides behind the fantasy: energy. Every form of advanced travel pays an energy bill. A sailing ship pays it with wind. A chemical rocket pays it with fuel. A nuclear spacecraft would pay it with reactions inside atomic nuclei. A laser sail pays it with a beam of light fired from far away. An FTL system, if it ever existed, would pay with something far more difficult to imagine. Not because energy is magic, because space-time is not a lightweight material. If a drive has to compress and expand space around a ship, then the engine is not simply pushing metal forward. It is arranging geometry. It is telling the local structure of the universe to take a shape it would not naturally take. Even a small distortion could require enormous control. A human-scale bubble large enough to hold a spacecraft, equipment, shielding, power systems, and crew would not be a laboratory curiosity. It would be an engineered region of curved space-time. That phrase sounds calm until you think about what it means. We know how to curve space-time by using mass and energy, because mass and energy are what gravity responds to. Earth curves space-time. The sun curves space-time more. A black hole curves it so severely that paths inward stop leading back out. But we do not know how to sculpt space-time freely like a material in a workshop. We cannot place curvature here and remove it there, on command. We cannot produce a stable shell of negative energy around a ship. We cannot store a star's worth of energy in a machine and expect ordinary engineering to survive. So the first faster-than-light spacecraft would not only be a vehicle, it would be the most extreme power plant ever built. It might need energy gathered over years, perhaps from solar arrays spread across space, fusion reactors, antimatter systems, or technologies beyond anything we have today. It might require materials that do not exist naturally. It might need cooling systems larger than the ship itself. It might need to dump waste heat into space without revealing its location, melting its own structure, or disturbing the bubble it is trying to maintain. Heat alone could become a nightmare. Every machine produces waste heat. On Earth, heat can move into air, water, ground, or other materials. In deep space, the main way to remove it is radiation. A powerful FTL engine would need to shed heat into the void, and if the ship is inside a strange space-time geometry, even that simple process could become complicated. Where does the heat radiate? Does the bubble trap some wavelengths? Can radiators extend through the boundaries safely? Does the drive operate only in bursts because the ship must cool down between jumps? A practical, faster-than-light civilization might not fly constantly. It might jump, drift, cool, check systems, then jump again. That version feels less like smooth science fiction and more like crossing a dangerous ocean in stages. The route between stars could be marked by safe zones, cooling points, navigation beacons, and forbidden regions. A ship might spend days preparing for a jump that lasts seconds. Crews might fear the quiet period before activation more than the motion itself, because that is when every system must agree. The engine, the clock, the map, the shield, the radiation monitors, the causality software, the life support, the emergency shutdown system. Everything must agree. One bad reading could mean waiting. One failed sensor could cancel the trip. One incorrect mass estimate near the destination could make the difference between a safe emergence and an arrival too close to a planet, a comet cloud, or a star's outer atmosphere. This would make faster-than-light travel psychologically different from the way we usually imagine it. The passengers might not feel speed. They might feel procedure, checklists, delays, silence. Crew members speaking softly, because everyone understands that the ship is about to do something no animal body evolved to experience. Then, a transition. Then, another sky. If the technology is reliable, people may eventually become used to it. That is what humans do. We become familiar with miracles. The first airplane was terrifying. Now people complain about legroom. The first orbit was almost unimaginable. Now satellites quietly guide cars through traffic. If FTL became routine, future children might treat interstellar travel as normal. But normal does not mean safe. Air travel became routine because millions of flights taught engineers what could go wrong. FTL travel would have to learn from failures too. Some ships might vanish without explanation. Some might arrive damaged. Some might appear slightly off course. Some might experience clock anomalies, radiation spikes, or communication problems that engineers spend decades trying to understand. The early age of faster-than-light travel could have its own ghost stories. A ship that returned with its onboard logs corrupted. A probe that emerged near the wrong star. A mission that arrived safely, but with clocks shifted by a fraction of a second. No equation predicted. A vessel that transmitted one clean message from interstellar space and then never answered again. These would not prove supernatural mystery. They would be engineering data. But, to the people living through that era, they would feel like reminders that humanity was no longer dealing with ordinary machines. It was operating at the edge of the framework that makes machines understandable. That edge would shape culture. People might become divided between those who see FTL as liberation and those who see it as a violation. Some would say the stars are finally open. Others would say the light speed limit was a warning, not a challenge. Religious movements might interpret the breaking of cosmic distance as destiny, arrogance, or apocalypse. Philosophers would argue about whether a person who returns through a causality-altering route is still connected to the same history they left. Families would face choices no generation before them had faced. Do you let your child leave for a world whose present cannot be seen from Earth? Do you trust a drive that touches space-time itself? Do you move to a colony that may one day become politically unreachable, culturally distant, or physically cut off if the network fails? Do you accept that your descendants might be born under another star and never consider Earth their home? FTL would not only shorten travel, it would stretch identity. The word humanity might begin as one species on one planet, then become a scattered collection of related civilizations. Some would live on terraformed worlds, some in orbital habitats, some in underground cities around red dwarfs, some aboard ships moving between systems. Some might choose isolation, others might build dense networks of trade and communication. The galaxy would not become one society automatically. It might become a forest of human branches, and each branch would remember the breakthrough differently. To Earth, faster-than-light travel might be the moment the sky opened. To a colony, it might be the reason they exist. To a world damaged by careless exploration, it might be remembered as the technology that brought disaster. To a civilization born centuries later, it might simply be infrastructure. as ordinary as roads. That is how large changes vanish into daily life. They begin as impossible, become dangerous, become expensive, become regulated, become normal, and finally become invisible. If FTL ever reached that final stage, the most astonishing part would be how quickly people stop being astonished. But the universe would not stop being dangerous just because humans adapted. A ship crossing the galaxy faster than light would still be entering places shaped by stellar evolution, radiation, gravity, dust, magnetic fields, and time. The technology might bend distance, but it would not negotiate with a gamma-ray burst. It would not make a pulsar's beam harmless. It would not turn a dead world into a home. It would not make an alien biosphere safe to breathe. It would not make human beings immune to fear, ambition, grief, or error. So the real question is not simply whether faster-than-light travel could happen. The deeper question is what kind of species would be responsible enough to survive it. And that is where the second half of the journey has to go. Because if humans actually crossed the light barrier, the story would no longer belong only to physicists and engineers. It would belong to everyone who lives in the new universe created by that discovery. And the first people to discover that new universe would probably not feel like conquerors. They would feel like survivors. Because the first faster-than-light journey, if it ever happened, would not be a clean jump from one shining star to another. It would be a test of every assumption humans had ever made about distance, danger, time, and control. A ship might cross a gap that light itself could not cross in the same amount of ordinary time, but the crew inside it would not suddenly understand everything waiting on the other side. They would not arrive with perfect maps. They would not know whether the space ahead was quiet or full of invisible debris or passing through a region shaped by an old stellar explosion. They might leave with calculations, models, telescopic surveys, and years of planning. But when the bubble opened, or the shortcut ended, or whatever form the journey took finally released them back into normal space, they would still have to face the oldest rule of exploration. Arriving is not the same as being safe. That is the first terrifying thing faster-than-light travel would change. It would not remove the unknown. It would make the unknown easier to reach. Imagine a ship leaving the solar system for a star hundreds of light years away. Without faster-than-light travel, that star is not a destination. It is almost a symbol. It exists in our sky, but for human lifetimes it might as well be part of a painting. Light travels from it to Earth. Telescopes study it. Spectrographs break its glow into chemistry. Computers estimate the planets around it. We learn from a distance. We wait for photons. But if humans could actually travel there faster than light, the relationship would change. The star would stop being only an object of astronomy. It would become a place. And places are dangerous in a different way than lights in the sky. From Earth, a star system can look calm because we only receive a softened, delayed, incomplete version of it. The light that reaches us is already old. A planet may appear stable in transit data, but we may not know its surface radiation. A disk of dust may be too faint to map fully. A quiet star may still produce flares strong enough to sterilize a close planet. A beautiful nebula may contain high-energy particles, shock fronts, and magnetic structures that do not care how advanced a spacecraft is. Distance hides detail. Faster-than-light travel would let us reach detail before we fully understood it. So the first FTL navigators would need to solve a strange problem. They would need to travel to places faster than information from those places can naturally reach them. That sounds simple until you really sit with it. In ordinary space travel, light is the messenger. If something changes ahead of you, light from that change eventually reaches your instruments. If a star erupts, if a collision happens, if a cloud of debris shifts, that information travels outward at light speed. But if a spacecraft can cross distance faster than light, then the ship can arrive before the warning does. It can overtake the news of danger. A system that looked safe from Earth might not still be safe when the ship arrives. A planet observed 200 years ago might have suffered an impact 100 years ago, and Earth would not know yet. A star might have flared violently decades after the light we used to plan the mission. An alien civilization might have risen, collapsed, or changed beyond recognition during the delay between observation and arrival. In a galaxy where light takes time to speak, faster-than-light travel would let humans step into conversations before they have heard the latest sentence. This would make navigation less like driving and more like entering a dark room based on a photograph taken years earlier. Even if the ship used a warp bubble rather than physically accelerating through space, it would still need a way to decide where to emerge. The destination would have to be calculated not as a fixed point, but as a moving arrangement of stars, planets, debris, and gravitational fields. Every star is moving. Every galaxy rotates. Every planet orbits. Every moon shifts. A mistake of a fraction of a degree over hundreds of light years could place the ship far from its target, inside a hazardous region, or simply lost in ordinary darkness with no easy way to orient itself. The galaxy is not a frozen map. It is a moving storm of matter. And if the ship emerged too close to a star, too near a magnetically active region, or inside the path of a dense dust stream, faster-than-light travel would become a very short miracle, followed by a very old disaster. This is why the most important instruments on an FTL vessel might not be the engines. They might be the sensors. Before each arrival, the ship would need to listen. It would need to check the local radiation environment, map nearby mass, locate dust concentrations, compare star positions with old records, and confirm that the space ahead is not occupied by anything larger than a harmless particle. In fiction, faster-than-light travel often feels like opening a door. In reality, if such travel were ever possible, the door would need 1,000 locks, alarms, and emergency brakes. A tiny mistake would not feel tiny at interstellar scales. A grain of dust is not impressive on Earth. You brush it off a table without thinking. But at extreme relative velocities, small objects become destructive. Even without a ship moving locally faster than light, any transition into normal space could produce dangerous encounters if the ship is not carefully matched to its surroundings. Microscopic particles can damage spacecraft today. In deep space, with higher energies and fewer chances for repair, the environment becomes a patient enemy. FTL would not cancel that. It would add new ways to meet the problem. If a warp bubble collects radiation or particles at its front edge, then arrival itself could become dangerous. Some theoretical discussions imagine energy building around the bubble and releasing when the ship stops. Even if the exact physics is uncertain, the basic fear is easy to understand. Distorting space-time is not like sailing across calm water. It means changing the geometry through which energy, matter, and light move. The boundary of such a system would not be a decorative effect. It would be part of the machine, and the machine would be touching the universe. That means the first FTL ship might arrive not quietly, but violently. A destination might receive a burst of radiation before the crew even speaks. A safe arrival near an inhabited world could require stopping far outside the system, perhaps beyond the orbit of distant comets, then approaching slowly by conventional propulsion. The most advanced journey in history might end with the crew waiting weeks or months before they could safely come close to the place they crossed the galaxy to reach. That delay would feel strange. Humans might beat light across interstellar space, then be forced to move patiently once they arrived, because planets, atmospheres, and living worlds are delicate. The hardest part of FTL might not be speed. It might be restraint. The next consequence would be even more unsettling. Faster-than-light travel would break the emotional meaning of distance, but it might not break the physical meaning of time. On Earth, we are used to time being shared. We argue about time zones, schedules, delays, and calendars. But beneath all of that, we feel that the present is something everyone inhabits together. The sun rises at different hours, but the world is still one world. Messages cross oceans in fractions of a second. A disaster in one country can be seen by another almost immediately. We live inside a global now. Interstellar civilization would not have that. Even without FTL, separate colonies around other stars would live under delayed light. A message from a colony 10 light-years away would take 10 years to arrive. A reply would take another 10. Politics, grief, science, trade, and family life would all happen through enormous delay. Faster-than-light travel might seem to solve this. Ships could carry messages faster. People could visit. Emergency medicine, supplies, and news could move across the stars. But once motion or information moves faster than light, relativity complicates the idea of a shared now. Different observers moving relative to one another can disagree about the order of distant events. This is not a mistake in their clocks. It is built into the structure of space-time. For ordinary slower-than-light travel, that disagreement does not allow causes to outrun effects. Everyone still agrees that a signal cannot be received before it was sent in any useful causal sense. The light speed limit protects the order of events. If humans could send ships or information faster than light, that protection might weaken. A journey that looks like a simple shortcut from one frame of reference could look like something stranger from another. Under some conditions, an FTL signal can appear to arrive before it was sent. That is where the nightmare of causality begins. It is not just time travel in the dramatic sense of stepping into the age of dinosaurs. It is the possibility that communication itself becomes tangled with its own cause. A warning might arrive before the danger that caused it. A command might be received before the decision to send it. A rescue ship might launch because a colony sent a distress call, while in another frame, the rescue seems to arrive before the colony transmitted anything. For human beings, this would be more than a physics puzzle. It would become a legal, moral, and psychological problem. Who is responsible for an event if information about it can move in ways that different observers order differently? How do courts handle evidence when timestamps depend on reference frames? How do governments coordinate military decisions when one observer's future warning is another observer's impossible message? How do families understand a goodbye if the ship that carries it can return with news from a chain of events that does not fit ordinary intuition? Faster-than-light travel might force civilization to build a new kind of time law. Not just calendars, not just clocks. Law would have to define which frame counts for contracts, warnings, ownership, rescue obligations, and crimes. A colony might say a message arrived too late. Earth might say it arrived before the event. A ship might record a sequence that no planet agrees with. Entire institutions could be built around preserving causal order, verifying signal paths, and preventing dangerous loops. In that future, a traffic controller would not only ask where a ship is going, they might ask when its arrival is allowed to be true. This is one of the reasons real faster-than-light travel is so difficult to treat as just a faster engine. It is not only about crossing distance. It touches the architecture that lets cause and effect remain stable. A universe where causes reliably come before effects is a universe humans can plan inside. If FTL creates even small cracks in that structure, then the cost is not only energy, the cost is trust in sequence. And sequence is how minds survive. A person can endure danger if they understand before and after. You make a choice. The choice has consequences, and the consequences become memory. If the order starts to blur, fear changes shape. It is no longer only fear of death, distance, or failure. It becomes fear that reality itself has stopped behaving like a story. That is why an advanced FTL civilization might forbid certain routes. It might not be because those routes are physically impossible. They might be possible in the same way that an unstable bridge is possible. You can step onto it. That does not mean you should. Some paths through space-time might allow closed loops, paradoxical signal chains, or dangerous timing differences between moving systems. The safest faster-than-light network might be one where ships can travel only between approved gates, with strict synchronization rules and long waiting periods. The most powerful technology ever invented might feel less like freedom and more like a railway controlled by priests of causality. Every jump logged, every clock compared, every route certified, every unusual arrival investigated before anyone celebrates. Because the nightmare would not be a ship disappearing. The nightmare would be a ship returning with information that should not exist yet. Now imagine what that would do to exploration. At first, humans would probably use FTL cautiously. We would send probes before people. We would test short jumps inside the solar system, then between nearby stars, then toward more distant regions. Each step would require proof that the ship arrived where expected, when expected, without dangerous radiation release, without causality violations, and without losing contact with home. But humans are not patient forever. Once a technology works once, pressure builds. Scientists want data. Companies want profit. Governments want strategic advantage. Colonists want land. Desperate people want escape. Explorers want to be first. The first safe crossing would become the argument for the second. The second would become the excuse for the 100th. A machine that can shrink the galaxy would not remain a laboratory instrument for long. And that is where society would change. Before FTL, the galaxy is naturally protected by distance. Stars are not just far away. They are separated by time. A civilization cannot easily spread mistakes across the Milky Way. A war remains local. A disease remains local. A failed government remains limited by propulsion. Even signals spread only at light speed, giving the universe a kind of built-in quarantine. Faster-than-light travel would weaken that quarantine. A dangerous idea could move faster. A biological contaminant could cross between worlds if protocols failed. A weapon could be delivered without the long warning times ordinary physics provides. A collapsing colony could send refugees across huge distances. A conflict between two star systems could escalate before either side fully understood what happened. The same network that saves people could spread disaster. That does not mean FTL would be evil. It means speed removes buffers. On Earth, we learned this with ships, trains, aircraft, and the internet. Every faster connection gave humans more power to help each other and more power to harm each other. Medicine moved faster. So did invasion. Knowledge moved faster. So did propaganda. Relief supplies moved faster. So did disease. Faster-than-light travel would be the same pattern projected onto the stars. The galaxy would become smaller, but not necessarily safer. A distress call from a colony around Tau Ceti could bring help in days or weeks instead of decades. A failing habitat could be evacuated. A medical breakthrough discovered near one star could save children under another. A probe could visit an exoplanet and return samples to laboratories while the scientists who launched it were still alive. The emotional value of that is enormous. For the first time, human decisions about other stars would not have to be gifts to future generations. The people who began a mission might see its results. That alone would change science. Astronomy would become fieldwork. Exoplanets would no longer be shadows crossing a star or chemical hints inside distant light. They would become surfaces, skies, oceans, storms, glaciers, deserts, magnetospheres, and fossils. We could compare Earth to thousands of worlds not only by remote observation, but by direct exploration. We could learn whether life appears easily or rarely. We could find dead biospheres, young biospheres, strange biochemistries, or silence so complete it would make Earth feel even more impossible. But every answer would carry risk. If humans reached a living world, the first question would not be whether we could stand there. It would be whether we had the right to touch it. A planet with microbes would not look dramatic from orbit. There may be no forests, no animals, no cities, no obvious face of alien life. It might be a cold ocean beneath ice, a wet layer underground, or a thin film of organisms in mineral cracks. To careless explorers, it could look like an empty resource. To scientists, it would be one of the most important discoveries in history. To the organisms themselves, if they have no minds at all, human arrival would still be an event capable of changing their entire world. Faster-than-light travel would make planetary protection harder because it would make access easier. When Mars is hard to reach, every mission is slow, expensive, and heavily planned. If a living exoplanet became accessible, the temptation would be intense. Governments would want flags. Companies would want materials. Religious groups might want meaning. Tourists might want experience. Scientists would want purity. Settlers might want a second Earth. Each group would see the same world through a different desire. And desire is dangerous when distance no longer stops it. So the first FTL age might have to invent cosmic environmental law. Not as an idealistic extra, but as a survival tool. Some planets would be closed forever. Some systems would allow only sterile probes. Some biospheres might be observed from orbit for centuries before anyone lands. A civilization mature enough to cross the light barrier would have to decide that not every reachable place is a place to claim. That might be the hardest test. Not engineering, restraint. Because the ability to arrive quickly can create the illusion of permission. If humans can reach something, we often begin to believe it is meant for us. Space might punish that assumption. An alien microbe might not infect humans in a dramatic movie-like way. It might simply destroy a crop species, alter a closed habitat, clog filters, or react unpredictably with Earth biology. Earth microbes might do the reverse, overwhelming a fragile alien environment that evolved without defenses against our chemistry. Contact between biospheres would not need monsters to become catastrophic. It would only need ignorance. Faster-than-light travel would turn ignorance into a moving force. That is why some of the most important FTL ships might be boring. Quarantine vessels, laboratory carriers, slow inspection craft, automated sterilization platforms, legal sensor arrays around protected worlds. The future of interstellar civilization might depend less on heroic captains and more on patient people refusing to open doors too quickly. But even if humans were careful with alien life, there would be another kind of life to consider. Human life. A galaxy with FTL would change what it means to be born somewhere. Today, Earth is not just our home, it is our boundary. Every human birth happens under one sky, inside one biosphere, inside one gravity field. Even astronauts return to Earth or orbit close enough to remain connected. If faster-than-light travel allowed colonies around many stars, human identity would begin to split. Children born under red dwarfs, orange stars, binary systems, artificial habitats, and distant moons would grow up with different day lengths, different skies, different hazards, and different histories. They might still call themselves human, but would they feel like Earth was home? To someone born on a world where the sun is only a historical star, Earth might become more like an origin myth than a homeland. It would be the place humans came from, not the place they belong. Faster-than-light travel could keep colonies connected, but connection is not the same as sameness. Languages drift, cultures change, bodies adapt through medicine, environment, and maybe eventually genetic engineering. The farther humans spread, the harder it becomes to say where humanity is located. The light barrier currently gives that question a simple answer. Humanity is here. FTL would make the answer plural. That sounds beautiful, and maybe it would be. But it would also create loneliness on a new scale. Not the loneliness of being unable to reach another star, but the loneliness of becoming strangers to your own species. A person from Earth might visit a colony and find humans who laugh differently, fear different things, worship different histories, and consider Earth politics irrelevant. A person from a distant habitat might visit Earth and feel trapped by its gravity, weather, crowds, and old emotional weight. Faster-than-light travel might connect worlds while revealing that connection does not prevent separation. There is also the problem of power. Any technology capable of moving ships across interstellar distances faster than light would require enormous control over energy, space-time, or both. Even if later versions became efficient, the underlying capability would be profound. A civilization that can shape space-time for travel may also shape it for other purposes. It could move materials, shield regions, hide objects, weaponize arrival points, or manipulate access to entire systems. The first question would be, who owns the routes? On Earth, whoever controls roads, ports, canals, railways, airspace, satellites, and internet cables controls more than transportation. They control trade, security, migration, information, and opportunity. Interstellar FTL routes would be even more important. If travel requires gates, stations, exotic matter, stabilized wormholes, or carefully maintained space-time corridors, then those who maintain them could become the most powerful institutions in history. A planet cut off from the network might be effectively exiled. A colony granted a route might thrive. A government that can close a corridor could influence entire star systems without firing a shot. In that sense, faster-than-light travel might not create a free galaxy. It might create a gated one. Some worlds would sit near major routes and become wealthy. Others would remain remote, visited rarely, dependent on long chains of permissions and maintenance. The shape of civilization would be determined not only by stars and planets, but by the geometry of allowed shortcuts. A map of the future galaxy might look less like a smooth spread of settlement and more like glowing knots connected by dangerous threads. And every thread would need trust. If a wormhole is used, who guarantees the mouths remain stable? Who prevents one side from moving in a way that creates time problems? Who inspects the structure? Who decides when it must be shut down? If a warp corridor is used, who monitors energy buildup, navigational drift, or hostile interference? If ships can jump independently, who tracks them? Who stops pirates, smugglers, or desperate militaries from using the same freedom everyone else depends on? The deeper humans move into speculative propulsion, the more the dream becomes political. Technology does not erase power, it changes the shape of power. That would be another terrifying consequence. Faster-than-light travel is usually imagined as liberation from distance, but it could also become the greatest border system ever built. The galaxy might open, then immediately be divided by access, wealth, safety codes, treaties, and fear. The stars would not belong equally to everyone just because they became reachable. And then there is war. It is unpleasant to think about, but any honest exploration of FTL has to include it. A civilization that can move faster than light can move faster than warning. Depending on the technology, an attack might arrive before ordinary sensors detect the launch. A fleet could appear near a system, with little natural notice. Even if strict rules require ships to emerge far from inhabited worlds, rules work only when everyone obeys them. The light speed delay that currently protects distant civilizations from immediate conflict would be weakened. This could create a universe of suspicion. Every arrival point would be watched. Every unscheduled jump would be treated as a possible threat. Peace would depend on verification systems, automated defenses, diplomatic channels, and perhaps shared control over FTL infrastructure. Civilizations might avoid settling too close to major routes. Habitats might hide in distant orbits. Systems might build decoy stations. Even exploration vessels could be viewed as military probes. The ability to cross space quickly might make trust slower. That irony matters. A slower-than-light galaxy forces civilizations to think in long terms. Messages take years. Wars across stars are difficult. Empires struggle with delay. FTL makes coordination easier, but it also makes domination more practical. The same speed that lets medicine arrive in time could let violence arrive before diplomacy. Human history suggests that any powerful transport technology becomes part of conflict. Ships became warships. Aircraft became missiles before they became deep space probes. There is no reason to assume faster-than-light travel would remain pure. A mature civilization would need to design peace into the system from the beginning. Not hope, it appears afterward. But perhaps FTL would be so difficult, so expensive, and so fragile that it could never be used casually. That possibility is important. Maybe faster-than-light travel, if possible at all, would not become a personal convenience. It might never be like buying a ticket. It might be closer to building a cathedral, launching a moon mission, and operating a particle accelerator all at once. A single trip could require planetary-scale energy, years of preparation, and an infrastructure spread across a star system. If so, the galaxy would not instantly become crowded. It would open slowly, through rare, monumental crossings. That version is less chaotic, but still strange. In such a future, the first FTL voyage might be remembered for centuries. Not because it made travel easy, but because it proved the impossible was not protected by nature in the way humans thought. People might still live their entire lives on one planet, but they would know that distance had been wounded. The psychological effect could be larger than the practical one. For thousands of years, the stars have been unreachable by human bodies. We could imagine them, measure them, name them, and dream of them. If one ship crosses the gap even once, the sky changes. Not visually. The stars would look the same, but the mind behind the eyes would know something new. Those points of light are not only distant, they are reachable, and reachability changes mythology. A child looking up after the first FTL journey would not see the same sky their ancestors saw. They would see possible destinations, possible dangers, possible homes, possible graves. A star could become a rumor. A nebula could become a warning. A dark region could become forbidden. Constellations might stop being patterns and become travel sectors. The ancient sky would become a map. That is beautiful. It is also a loss. Mystery would not disappear, but it would move. The nearby stars would lose some of their sacred distance. Places once unreachable would become complicated instead of impossible. Wonder would survive, but innocence would not. The galaxy would stop being only something above us and become something we are responsible for entering. Responsibility changes wonder. The first humans to travel faster than light might return with samples, images, recordings, and stories. They might show an ocean under an orange star, a frozen rogue planet lit by artificial lamps, a brown dwarf with storms larger than Earth, or a lifeless world where the rocks preserve chemistry older than the solar system. Their discoveries could transform science, but they might also return changed in ways harder to measure. They would have crossed a boundary no human nervous system evolved to understand. Not merely distance, the meaning of distance. Astronauts today often describe the overview effect, a shift in perspective after seeing Earth from space. They see the planet as small, fragile, borderless, and alive. An FTL crew might experience something beyond that. They might look back not from orbit, not from the moon, not from Mars, but from another star, knowing that the sun is now one light among many, and that the distance between home and ship would have been impossible for almost all of human history. What would that do to memory? A person might remember a childhood street, and then step outside under a different star only weeks later. They might feel homesick for a planet that is physically close by the new technology, yet emotionally impossibly far. They might know they can return, but also know they have become someone who has seen home from outside its ancient isolation. Faster-than-light travel would not only expand geography, it would expand grief, because leaving would become easier. That sounds like a gift, until you realize what it means. Families could scatter across star systems. Some would return, some would not. Some would leave for a colony and die under another sun. Some would send messages through routes that later close. Some would be lost, not because stars are unreachable, but because choices, politics, accidents, or time made them unreachable in a different way. The universe might become smaller while human separation becomes more complex. And then there are the people who would never go. Most humans might remain on Earth, or on a few settled worlds, watching others cross the galaxy through screens. They would live in ordinary gravity, work ordinary jobs, pay ordinary bills, and hear about faster-than-light journeys as news. The greatest technology in history could exist alongside ordinary boredom. That is how humans are. We turn miracles into infrastructure, then complain when the infrastructure is late. This does not make the miracle smaller. It makes it more believable. If FTL ever becomes real, it will not always look cinematic. It will involve maintenance schedules, failed seals, insurance disputes, medical clearances, training manuals, uncomfortable seats, docking delays, political arguments, contaminated samples, and people asleep during the most astonishing crossing ever made. The future is often less dramatic than the dream, and more complicated than the nightmare. But the underlying fact would remain staggering. Humanity would have found a way to move through the universe in a manner that ancient physics seemed to forbid, whether by bending space, using shortcuts, manipulating geometry, or discovering some deeper layer of reality. The result would be the same from a human point of view. The prison of distance would no longer be absolute. And once an absolute boundary becomes negotiable, the mind starts asking what other boundaries might also be misunderstood. That could be inspiring. It could also be dangerous. A civilization that breaks one cosmic rule may begin to believe all limits are temporary. That attitude can produce discovery. It can also produce arrogance. The universe is full of limits that are not moral lessons or technological challenges. Some are simply facts. Radiation kills. Gravity crushes. Vacuum suffocates. Time passes. Entropy increases. Stars die. Black holes do not return what crosses their horizons. Faster-than-light travel, if possible, would not repeal all of this. It would only give humans a new way to meet it. So what would actually happen if humans traveled faster than light? At first, probably fear. Not screaming fear. Quiet fear. The kind that sits inside mission control while numbers appear on screens and no one knows yet whether the ship has survived. The kind that fills the crew cabin before the first transition, when every person aboard understands that theory has become hardware, and hardware is about to test reality. The kind that waits after arrival while sensors confirm whether the ship is intact, whether the destination is correct, whether time has behaved, whether the universe has allowed the impossible without demanding immediate payment. Then, if the ship survives, there would be silence. The crew would look outside and see a different star. That moment would be almost impossible to describe. Humans have visited the moon. Our machines have landed on Mars, Titan, comets, and asteroids. Probes have crossed the heliopause. but every human body that has ever lived has remained bound to the sun. Faster-than-light travel would end that ancient confinement. For the first time, a human being could stand inside a spacecraft and know the sun is no longer the star holding their life directly. A new star would be the local sun. A different gravitational architecture would hold the planets. The constellations would be rearranged. Earth would be absent from the sky, not because it is hidden by weather or daylight, but because it is too small and too far to see. That is the emotional core of FTL. Not speed, displacement. A human mind evolved to navigate forests, rivers, coastlines, storms, faces, and seasons. It did not evolve to change stars. It did not evolve to treat the sun as a former address. If humans actually traveled faster than light, the greatest shock might not be scientific. It might be psychological. The realization that home can become local history. The crew would still carry Earth inside them. Language, biology, memory, food, music, fear, love, and habit would all come from one planet. But outside the hull, the universe would no longer reinforce that origin. There would be no familiar moon, no familiar sunrise, no blue planet nearby, just another system, real and indifferent. And if they could make that journey once, they would know others could follow. Exploration would become migration. Migration would become history. History would become divergence. That is how one successful crossing could eventually reshape the species. But there is another possibility, darker and perhaps more realistic. The first FTL crossing might not lead to a grand expansion. It might prove that the technology is possible, but almost unusable. The ship survives, but the energy cost is absurd. The causality risks are too severe. The arrival hazards are too unpredictable. The political danger is too great. The machine works, but only once, or only under conditions so narrow that it remains a scientific monument rather than a doorway. That would be its own kind of torment. To know that faster-than-light travel is possible, but not practical, would be like seeing a locked ocean from inside a desert. The universe would have admitted that the wall contains a crack, but not one large enough for civilization to pass through. For generations, people would argue over whether to try again. Some would call it destiny, others would call it madness. The single successful flight might become myth, evidence, obsession, or warning. In that version, the question changes. Not what happens if humans travel faster than light forever. What happens if humans do it once and then realize the universe barely allowed it? That might be more terrifying than failure. Failure is clean. You try, you cannot, and the boundary remains. A partial success haunts. It tells you the impossible is not impossible, but also not yours. It opens a door wide enough to see through, not wide enough to walk through safely. Civilizations could spend centuries chasing that door. They might build larger engines, deeper theories, stronger materials, and stranger experiments. Some would succeed, some would vanish. Some might create disasters in laboratories, bending space-time in places not designed to be bent. Some might produce tiny artificial horizons, exotic energy configurations, or unstable wormhole mouths that collapse before any probe can pass through. The road to faster-than-light travel, if it exists, may be littered with attempts that teach more about danger than motion. Even the knowledge itself could be hazardous. Once a theory shows how to manipulate space-time for travel, it may also reveal ways to manipulate it for containment, communication, concealment, or destruction. Fundamental physics is rarely single-use. Nuclear physics gave us power plants, medicine, weapons, and stars understood in human equations. Relativity gave us GPS corrections, black hole physics, cosmology, and the understanding that time is not universal, An FTL theory would likely spill into many fields. The first warp engine might not be the most important invention. The instruments created to test it might change energy, gravity, astronomy, and communication before a single human ever leaves the solar system. That is another realistic outcome. The pursuit of FTL may transform humanity, even if the ship never works. Trying to break the light barrier could force deeper understanding of quantum fields, vacuum energy, space-time geometry, and gravity. The dream might fail as transportation, but succeed as science. It might teach us why the barrier is stronger than imagined. It might reveal new limits. It might even show that nature protects causality more deeply than current theories describe. Sometimes, the greatest discovery is not the road, it is the locked gate. If that happens, then faster-than-light travel becomes a mirror. It shows humans how much we want the universe to be smaller. We want travel to match desire. We want distance to surrender to imagination. We want the stars to become places our stories can reach within a human lifetime. And maybe that desire is part of what makes us explorers. But the universe does not owe us human-sized distances. That is the truth underneath every warp-drive dream. Space is large on its own terms. Light is fast on ours, but slow against the galaxy. A beam leaving Earth tonight will need more than 4 years to reach the nearest star. Tens of thousands of years to cross a small fraction of the Milky Way, and millions of years to reach nearby galaxies. That delay is not a technical inconvenience. It is part of the universe's structure. It shapes what can know what can influence what, and how separated events remain separated. To travel faster than light would be to interfere with that structure. Maybe gently, maybe disastrously. If it worked, the universe would become more intimate and more dangerous at the same time. Stars would become destinations, but destinations would carry responsibility. Aliens, if they exist, would no longer be only signals or speculation. They might become neighbors. The past and future might require new definitions. War and rescue would accelerate. Science would become direct. Mythology would collapse into logistics. Humanity would grow larger and less unified. And the night sky would never mean the same thing again. Tonight, the stars are mostly unreachable. That distance gives them a kind of peace. We can look at them without having to decide what to do with them. We can dream without consequence. We can imagine worlds without touching them. We can receive ancient light and leave the source undisturbed. Faster-than-light travel would end that innocence. The stars would become choices. Some choices would save lives. Some would create homes. Some would expose human weakness on a galactic scale. Some would be wise. Some would be unforgivable. The terrifying part is not only that humans might travel faster than light, it is that if we ever do, the universe will not simply become open. It will become accountable. Every crossing would ask what kind of species we are. Every arrival would test whether intelligence can move faster than fear. Every shortcut would remind us that distance was not just an obstacle, it was also a protection, a pause, a silence between worlds. To remove that silence is to accept everything that comes through it. There is one more consequence that is easy to miss because it sounds too ordinary. Economics would change. Not money in the simple sense, but value itself. Today, rare things are often rare because of location. A mineral deposit exists in one country. A telescope sits on one mountain. A launch site has one geography. A planet is the only planet we can reach with living people. Distance creates scarcity. Faster-than-light travel would not end scarcity, but it would rearrange it. If thousands of star systems became accessible, raw material might become less important than control, knowledge, timing, and safety. Metals, ice, carbon, ammonia, and silicates are common in space. The rarest thing might be a stable habitat, a protected biosphere, a verified route, or a trusted navigation model. A world with life might become priceless precisely because it cannot be used freely. A dead system rich in asteroids might become valuable because it can be used without moral conflict. A quiet red dwarf could become more important than a brilliant blue star because it lasts longer and behaves more gently. FTL would teach humanity that abundance is not the same as permission. The galaxy contains more matter than any civilization could easily imagine, but not all of it should be mined, settled, altered, or disturbed. Some places would be scientifically sacred. Some would be culturally sacred. Some would be too hazardous. Some would be politically disputed. The dream of infinite resources might run into the old human problem of deciding who gets access, who pays the cost, and who lives with the consequences. Even time would become a resource. A ship that can make one crossing per month is very different from a ship that can make one per year. A gate that requires decades to build can shape the fate of a colony before it ever opens. A route that closes during certain stellar conditions might create seasons of isolation. Markets, families, migrations, and emergencies would all adapt to the rhythms of the FTL system. People would not simply ask how far away a world is. They would ask how often it can be reached, how safely, under whose authority, and at what risk to everyone nearby. The map of civilization would become a map of reliability. Reliable routes would gather people, unreliable routes would gather legends. Systems cut off by failures might become ghost stories. A colony that misses 3 scheduled ships might trigger panic across the network. A gate that flickers during a storm of space-time instability might become the center of political crisis. The old fear of being alone in the dark would return. But now, it would happen inside an age that believed it had defeated distance. That may be one of the most human outcomes of all. We might build a machine to cross the galaxy and still spend our nights afraid that someone we love will not arrive. There would also be the question of memory. A species that can travel between stars faster than light might begin to forget how impossible the journey once felt. This happens with every successful technology. The first ocean crossings were terrifying. Later, oceans became trade routes. The first flights were miracles. Later, airports became places where people complain about delays. The first spacecraft were national events. Later, satellites became part of weather forecasts, navigation apps, and invisible daily systems. If FTL endured long enough, the same thing might happen to the galaxy. A child born centuries after the first crossing might treat another star as a place their relatives live. A classroom might display a map of nearby systems, the way schools once displayed maps of continents. People might argue about the best colonies, the safest routes, the most beautiful skies, the worst ports, the strictest quarantine rules. The impossible would become ordinary language. That would be wonderful. It would also be dangerous, because ordinary things are easier to disrespect. A culture that grows up with FTL may stop feeling the weight of what it is doing. It may forget that every route depends on delicate physics. It may forget that every biosphere is vulnerable. It may forget that a star system is not empty just because no one owns it. The first generation might be careful because the danger is fresh. The 10th generation might be careless because the system has always worked for them. Many disasters begin when a miracle becomes routine. So the survival of an FTL civilization might depend on memory as much as machinery. It would need rituals, education, laws, and stories that keep the danger alive in the imagination. Not to freeze people in fear, but to prevent the arrogance that comes when success lasts too long. Every advanced society needs ways to remember what its infrastructure is protecting it from. For a faster-than-light civilization, that memory would have to include the darkness between the stars. There is another, quieter possibility that would reshape the story before true FTL ever arrives. Humans might first master almost light speed travel. That would not be the same thing. A ship, moving at 90% of the speed of light, still obeys the old rules. It cannot outrun a light beam. It cannot send a warning into its own past. It cannot make distant events reorder themselves in the same dangerous way. But for the crew, time would begin to stretch. Their clocks would not match Earth's clocks. A journey that takes many years from the outside might feel shorter inside the ship. Relativity would become part of daily life, not as a diagram in a textbook, but as the reason birthdays, histories, and relationships no longer line up cleanly. Near-light travel is strange, but it is still inside the fence. Faster-than-light travel is what happens when humans try to step beyond the fence. That contrast would matter to the public. Some people would not understand the difference at first. If a relativistic ship can reach another star while the crew ages less, it may feel almost magical enough. Why risk warp bubbles, wormholes, causality problems, and exotic energy if slower methods already let people cross the stars? The answer would depend on who you ask. For scientists, FTL would be a fundamental discovery. For governments, it would be strategic mobility. For colonists, it would be supply and rescue. For families, it would be the difference between goodbye for generations and goodbye for a season. For a dying world, it might be evacuation. So even if near-light travel became possible first, faster-than-light travel would remain tempting. It would promise not only motion, but synchronization. It would promise that human lives and interstellar distances might finally fit inside the same emotional frame. That promise is powerful enough to drive centuries of effort. But promises are not physics. Physics is colder. It does not become friendlier because a civilization has a reason to need it. If exotic matter cannot exist in the required form, if quantum fields prevent stable shortcuts, if space-time resists the creation of safe warp geometries, then no amount of longing will make FTL practical. The universe may allow mathematics that resembles a door without allowing engineers to build a doorframe around it. That would be difficult for humans to accept. We are used to turning impossibilities into delays. Flight was impossible until it was not. Reaching the moon was impossible until it happened. Splitting the atom was unimaginable until it became one of the defining powers of the modern age. But not every barrier is that kind of barrier. Some are not waiting for better tools. Some are the shape of the world. The speed of light may be one of those shapes. And if it is, then every story about FTL becomes valuable not because it predicts the future, but because it teaches us what the present means. It reminds us that the galaxy is not designed around human patience. It reminds us that light, the fastest messenger we know, still takes years to cross the nearest stellar distances. It reminds us that the universe has scale so large that even our most ambitious machines may remain local for a very long time. Yet, if the barrier can be crossed, even indirectly, everything changes. The difference between impossible and almost impossible is the difference between a wall and a frontier. A wall can inspire poetry, longing, and acceptance. A frontier creates maps, arguments, mistakes, and graves. That is why the first confirmed faster-than-light journey would be one of the most important moments in human history. It would not only prove a machine worked, it would prove the galaxy had become a place where human action can arrive before human imagination has fully prepared for it. And that is exactly what makes the idea so dangerous. Human technology often advances faster than human wisdom. We learn how to do things before we agree on what they mean. We learn how to split atoms before we learn how to live with nuclear weapons. We build global networks before we understand what constant connection does to truth, attention, and trust. We change climates before we fully organize ourselves around the consequences. Faster-than-light travel would be another version of the same pattern, but written across the stars. The question would not be whether humans are clever enough. The question would be whether cleverness is enough. A species can be brilliant and reckless at the same time. It can calculate a space-time metric and still mishandle a living planet. It can build an engine that crosses 1,000 light-years and still argue over short-term power. It can map the galaxy and fail to understand itself. FTL would magnify everything human, not only our courage and curiosity, but our impatience, our rivalries, and our talent for turning gifts into tests. That is why any believable future of faster-than-light travel must include humility. Not the kind of humility that refuses to explore. The kind that understands exploration is not ownership. The kind that knows speed is not wisdom. The kind that can look at a reachable star and still ask whether reaching it now is the right thing to do. Without that humility, FTL would not make humanity cosmic. It would only make our mistakes travel farther. So perhaps the final answer is this. If humans actually traveled faster than light, we would not become gods. We would not escape physics, danger, loneliness, time, or consequence. We would become travelers in a universe whose scale we had partially defeated, but whose rules we still did not fully understand. We would gain the stars, but we would also inherit the responsibility of reaching them. And maybe that is why the light barrier feels so powerful. It is not only a speed limit, it is the line between looking at the cosmos and entering it. If we ever cross that line, the greatest discovery may not be what waits around another star. It may be what faster-than-light travel reveals about us.